Hello there, radio listeners and YouTube viewers tuning in. It's your host Nino coming at you live from England. Today's date is 2025, April 25th, a lovely Friday. Do you know what we do sometimes? We dig into the archives, find something cool and trending, and talk about it, right? So today I've got this paper, let me see. Here it is. The title is Speech Tokenization and Embedding for Spoken Language Modeling. The call is that spelled. It's not in archive link this time, but a GitHub one with the code and models. Nice. Okay, so taste. What's this all about? Well, you know these big AI models, large language models or LLMs. They're amazing with text, right? Writing emails, summarizing stuff, chatting. But they're kind of stuck in the text world. They write text, they write text. People want to add they can actually talk to them naturally. And have a talk back, not just like a robot reading text, but really speak. So researchers are working on spoken language models, SLMs. Models that can listen or talk. Makes sense. A big hurdle is mixing speech and text. They call it the modality gap. One major issue, speech is well-run and continuous. When you turn speech into digital tokens, you usually get way more tokens than if you just tokenize the text transcript of that speech. It's like saying, well, it might be one text token, but the sound wave could be dozens or hundreds of speech feature phones of tokens. This length mismatch makes it super tricky to train models that handle both smoothly. Previous attempts tried to reduce the number of speech tokens or use complex training strategies. But the mismatch problem can be stuck around. Enter TASTE. This paper says, hey, let's tackle this mismatch head-on. TASTE stands for Text-to Speech Tokenization and Embedding. The core idea is careful. Make the number of speech tokens match the number of text tokens for the transcript. Right from the start, go on tokenization. How would they do it? And involve some neat tricks. They use components like an enloader, often initialized from an existing speech recognition model, like Whisper. Then there's a special aggregation component. This uses the text transcription to guide how the speech features are grouped together, so the output speech representation naturally aligns lengthwise with the text tokens. And they train this whole thing using speech reconstruction as a goal. Basically, the tokens need to be good enough to recreate the original speech, including its nuances. The cool part is they claim this TASTE method preserves important paralinguistic information. You know, the stuff beyond the words, tone, emotion, rhythm. And it does this while dramatically shortening speech token sequence compared to other methods. They say it's the first thing time to put using this reconstruction idea to automatically align text or linear tokens perfect for songs. So once you have these TASTE tokens or embeddings, which are nicely aligned with text tokens, it becomes much easier to adapt the text-based LLM into a spoken one. They even tackled the issue with the speech recognition models. Vocabulary might differ from the LLM's vocabulary. They use some smart word level grouping and averaging to sort that out. Then, they can fine-tune a pre-trained text LLM like Llama. Using efficient methods like LLM, this means they would have to retrain the whole giant model from scratch. Big savings. The fine-tuned model learns to predict both the next text token and the corresponding TASTE speech token or embedding. How does it stack up? Well, compared to other speech tokenization methods, TASTE achieves really high-quality speech reconstruction, similar to others, but at an extremely low bitrate, like 10 times lower in some comparisons. That's huge. It means less data, faster processing, and when used in some models using TASTE performed really well on benchmarks. On tasks testing acoustic understanding, like detecting speaker or emotion changes the sampling benchmark, it did comparably to previous methods that needed full model training, even though TASTE used efficient line tuning. On tasks testing semantic understanding, like choosing the right story in the industry closed benchmark, actually did much better than some baselines, suggesting it helps the LLM retain its text understanding while learning speak. Right, so where could we see this kind of tech? Let's think. 3 examples. Voice assistants. Imagine Siri or Alexa, while just understanding your words, but responding with speech that genuinely matches the context's emotion or tone. More natural, less robotic conversation. That'd be nice, wouldn't it? 2. Game characters NAS. Instead of just reciting pre-rated lines, the dialogue could be generated on the fly using TASTE. Their speech could sound genuinely scared, excited, or bored, reacting damningly to the game. Much more science. 3. Content creation accessibility. His comparators for automatic expressive voiceovers for videos or podcasts, or maybe generate realistic dubbing for films in different languages preserving the original vocal style, could also help create better text-to-speech. For accessibility tools with more natural prosody. So taste seems like a really promising step towards bridging the gap between text AI and spoken AI. Making speech tokens align with text tokens for Nuances simplifies things a lot, leading to efficient training and models that can truly listen and speak with nuance. Pretty fascinating stuff brewing in Archives Eye. Alright, that's the scoop for today from my Mino news desk. Talking to myself as usual. Hope you found that interesting. Catch you next time.